A review on equilibrium in 2D. Today we're going to look through the application of vector methods and moments to the equilibrium analysis of engineering problems in 2D. Here are some of the learning outcomes. Understand and apply free body diagram principles. Analyze moments and couples in 2D systems. Solve 2-force and 3-force body equilibrium problems. And develop problem-solving techniques for 2D equilibrium. Now let's look at some review for Mechanics 1. In this section, we'll learn how to draw a free body diagram using the given beam setup as an example. Let's go through the key steps. First, identify and remove the supports. In the original diagram, the beam is supported at point A by a pin and at point B by a roller. Once removed, these supports are replaced with reaction forces. Next, we draw and label all forces acting on the beam. This includes the 6,000 Newton load applied downward at a distance of 0.6 meters from point A, as shown in the diagram. Don't forget to consider the weight of the beam if it's given or relevant to the problem. Finally, add the reaction forces from the supports. At point A, the pin provides both AX and AY, while at point B, the roller provides only BY. When you complete these steps, the resulting free body diagram should look like the image on your right. Now let's go over the different types of support and connections. A pin support can resist forces in both the X and Y directions, but cannot resist a moment. In our example, the pin has reactions at AX and AY. A roller can only resist a force perpendicular to the surface it rolls on, so it provides only one reaction force. In our example, there's only BY. A fixed support can resist forces in both X and Y directions and resist a moment. It's fully constrained. A cable can only resist tension forces along its length and cannot resist forces in other directions or moments. Lastly, we have our connections. We can either have a pin connection, which can transfer forces in X and Y, but not a moment, or a full moment connection, which can transfer forces and moments. This example operates in a simple X and Y coordinate system, but we can also have a different coordinate system like S and R. A moment is the tendency of a force to cause rotation around a specific point, and its direction, clockwise or counterclockwise, is determined by the force's orientation relative to the pivot point. So we associate the negative sign with clockwise and the positive sign with counterclockwise, which is caused by our right-hand rule. 2-force body. When there is only 2 forces applied on a rigid body, in equilibrium, 2 forces must be equal and opposite, and act along the same line of action. So if 2 forces are not acting along the same line of action, a couple will be formed. And remember, this is regardless of its shape. Next, a 3-force body. So when 3 forces are applied on a rigid body, in equilibrium, the 3 forces must be coplanar, concurrent, and form a closed triangle. Before we get into today's example problem, let's look at some 2D equilibrium problem-solving procedures. Let's bring back the example we used before, with the pin support and the roller support. First, let's start off by drawing our FBD, which is our free body diagram. Next, select an appropriate axis. Remember, it's not necessarily horizontal or vertical, but in our case, it will be. Third is select appropriate objectives to consider. So we can either consider a part of the structure, if we have a complex structure that is, or the entire structure. In our case, we're going to be considering the entire beam. 4 is eliminating all your unknowns. To make it simpler for us, we're going to eliminate all the reactions at point A by taking the moments at point A. This way we can solve for BY. Finally, write out the force and moment equation and solve for them, which is Fx is equal to 0, Fy is equal to 0, and our moments are equal to 0. Now for our example problem. Here's the scenario. We have a man in a personnel lift. The system consists of a boom arm and a bucket, along with the man himself. The boom has a center of gravity at G1, where its weight acts vertically downward. The bucket and arm have a center of gravity at G2, where their combined weight also acts downward. Finally, the man in the bucket has a center of gravity, with his weight acting downward as well. Our goal is to find the resultant moment about point A. Here's some hints to get started. feel free to pause the video and try this problem for yourself. Now let's draw out our free body diagram. Point A is at the base of the arm. The boom is 30 feet long, inclined at 75 degrees. The center of gravity for the boom is located 2.5 feet from the pivot at A. The bucket's center of gravity is located 1.75 feet beyond G1. The diagram shows all forces and its dimensions. Now to calculate the individual moments. Remember, moments can be found by multiplying the perpendicular distance by the force, which is the magnitude of the loads. So moment 1 is caused by the boom's weight acting at G1. That is 10 feet times cos 75 degrees, which is the horizontal distance. Multiply this by 1,500 pounds, which is the magnitude of the boom. This gives us a result of negative 3.88 kip feet, or 3.88 kip feet in the clockwise direction. Remember, we're taking moments about point A, and G1 creates a clockwise rotation around point A. Now let's do the same for moment 2 and moment 3. So moment 2 is caused by the bucket's weight acting at G2. So that is 30 feet times cos 75 degrees plus 2.5 feet. Multiply this by 200 pounds. This gives us negative 2.05 kip feet, or 2.05 kip feet in the clockwise direction. Again, G2 creates a clockwise moment about point A. Lastly, moment 3 is caused by the man's weight in the bucket. This is equal to 30 feet times cos 75 degrees plus 2.5 feet plus 1.75 feet. Multiply this by 175 pounds. This gives us a result of negative 2.10 kip feet, or 2.1 kip feet in the clockwise direction. Again, G3 also creates a clockwise moment about point A. Finally, let's find our resultant moment, which is m1 plus m2 plus m3. This gives us a result of negative 8.04 kip feet, or 8.04 kip feet in the clockwise direction. Remember that all forces create a clockwise moment, so they should be assigned a negative sign based on standard convention. In summary, we found our resultant moment to be 8.04 kip feet in the clockwise direction. Some key takeaways. Always start with a clear free body diagram. Use proper sign conventions for moments. Break this problem into smaller parts to simplify calculations.